Okay. Yeah, so good evening and welcome to today's class. Am I audible enough, Nelson?
Yeah, you are.
Okay, thank you. All right. So we want to introduce a very important concept in networking. And so far we have been talking about so much about switching. We talked about wireless networks, and we did some configurations for the switch, and we did as well for the wireless networks. It is now time to have this conversation around routing, right? So switching is done by switches, routing obviously done by routers, put together, of course, with the layer 3 switch. And we now want to do routing, and we check out some concepts that are found behind routing. And so some of the things we're going to study within routing include how routers are used to determine the best path within a network. It goes without saying that the layer 3 devices, like a router and the layer 3 switch, are the only devices that can connect one network and another network. And that is something very important to note, all right? So to connect your LAN and another LAN, or your LAN and the ISP, the device that can only do that is the router, or layer 3 switch for that matter. And so it's important for us to just get that. So we'll explain how routers forward packets to the destination networks or devices. We look at some basic settings on a router, and some of these are things we had already looked at before. We'll configure basic settings on a router, describe the structure of a routing table. Remember, during switching, we talked so much about the MAC address table of the switch. We talked so much about the MAC address table of the switch. When it comes to routing of the router, we are going to talk about yet another table, and this table is called the routing table, right? And then we'll compare both static and dynamic concepts, static and dynamic routing concept. So let's start by what's called path determination. And so the first thing to note is that when a router receives a packet, or a message on one of its interfaces, the routers will determine which interface to forward that packet. And in most cases, the process of transferring one packet, which is from another network, through one of the router interfaces to another interface within the router, this is what we call routing, okay? And it is important to note at this point that every router interface is connected to a different network or to a separate network. Every router interface is always connected to a separate network. And so that is why the routers are very special devices, because it is the only device that can connect your network to another network, okay? Switches, the layer 2 switches, all those, they work within the same network. But a router will connect your network to another network. And so the process of forwarding a packet that is entering one interface and forward it to another interface, to another network, is what's called routing, okay? And sometimes where the packet is forwarded can be the final destination network, or it can be another router, which, basically connects us to the destination network. And so the primary functions of a router, therefore, is to determine the best path to forward a packet. And this determination is based on information that is stored within the routing table of the router. And the other function is obviously is to forward packets towards their destination networks. So a router has the mechanism of forwarding the packet. If it is not the destination network, then it will forward it to the direction of the destination network. Very, very important for us to note. And so the routing table, which basically is used by the router to store routes, or we could call them maybe directions or something. Okay. So for example, a router in its routing table normally stores the routes to reach different networks. Okay. And these different networks, it could be a network that is directly attached to that router, or it could be a remote network, which means the router needs to go through another network to reach that network. That is called a remote network, and we are going to learn so much of it, today. Now, this very important term here, called the best path equals the longest march. This expression is very important. The reason why it is important is because the router uses it a lot. Okay. And so if the router has so many paths to reach a certain network, the router needs, and it knows how to choose the best path. Among all those paths available to reach network X, for example, the router is going to choose the most suitable path, and that will always depend on the subnet mask of the network of that path. And that's why the word longest match comes in place here. So the longest match basically means among the networks available, which one has the biggest subnet mask? And we did learn about subnet mask in the past course, Introduction to Networks. So normally the routing table contains these route entries, which consists of the network address and the prefix length, basically the network address and the subnet mask. And so every time a packet is received on a particular within the router is gonna, because that packet has a destination IP address. That's one of the components. And so that destination IP address is going to be used to compare with all the networks, all the routes that are stored within the routing table. And so if there are multiple routes going to the same destination, then the router chooses the route that has a larger subnet mask, and that is very, very important. So the subnet mask, which is also called the prefix length, is very, very important. And so the longest match, which basically means the longest match of the largest prefix length, is always the preferred one while reaching a certain destination network. Now, it is important to see some examples here. For example, looking at let's trying to get the looking at the table we have here, you can see that we have three network addresses with their subnet masks. So we have 172.16.0.0/12, 172.16.0.0/18, and 172.16.0.0/26. The IP address of the destination IP address of the packet. The packet actually is going to a network 172.16.0.10. That is the destination IP. And so since all these routes begin with 172.16, just like the destination, so this IP here is going to be checking among these routes available within the network, which one has the highest subnet mask, and obviously it is /26. So /26 has the longest match, okay? And when I talk about the longest match, I want you to note something. /26 means 26 ones, and the rest are zeros. You know that a subnet mask is made of ones and zeros, and the /26 means there are 26 ones and I think 6 zeros. Okay. And so if you can map every bit of the IP address with the 1 bit here, So the subnet mask with the highest ones, which is always the largest number here, will always be the best match for the network. And that is something the router does so on and so often than not. Now, a very simple question. How does the router build its routing table? Okay. How does it compute the routing table? That is a very, very valid question for us to ask ourselves. Because when the router is just new, the routing table is always empty. Okay. The routing table is always empty. But there are a few things that when they are done, it makes the routing table to begin populating itself. And those are some of the things, some of the concepts that I want us to look at right now. And so the first thing to note is this. I know that previously we have been learning how to configure IP address of our router interfaces. We've learned how to configure an IP address on the router interfaces and activate those interfaces. And so I want to submit to you that there are three ways of populating the routing table. The first way is the moment you configure an IP address on a router interface, okay? The moment you configure a router, an IP address on a router interface, that router interface, you activate it using the no shutdown command, okay? Automatically, the network address where that IP you have configured belongs will be recorded. The router knows how to calculate the network address from the IP and the subnet mask you have entered. In fact, the router uses the ANDing process. And so by just configuring a router interface with an IP and activating that interface, the router records that as a root within the routing table, okay? And that root is called a directly connected network. A directly connected network. So that is one way. Just assign IP addresses to the router interface and activate them. The routing table will be populated with the routes to reach those networks. Only that those networks, since they are interfaces that are directly attached on your router, they are going to be called directly connected networks. Then, since these ones are routes, it's a network that is attached to that router because they are on the router interfaces. What if these networks can only be reached through another router? What if this network, they're available, but they are not connected directly to our router, but our router is connected, let's say our router is router A. Then there's another router, router B, which is connected to our router. Now, on router B are also other networks. Okay. Router B also has its own directly connected networks. And I wanted to just get an example to explain to us this so that we can get it. Otherwise, it will not sync well. Let me use this example here. So looking at the diagram here, R1 has so this is network on switch S1. R1 is directly connected to switch S2. And the network is here. And R1 is also connected to R2. R1 is also connected to R2. And so we say that R1 is directly connected to 3 networks. And you can see that because R1 is attached to 3 different connections. And those ones are 3 networks. Since we said every router interface connects to a different network. Now, once we see that, you can also see that on R2. R2 is directly connected now to 4 networks. Okay. R2 is connected to R1, R2 is connected to S3 LAN, and R2 is connected to S4. Okay. And so those are our directly connected networks of R2. So my question is this. If we are in R1, and being in R1 has 3 directly connected networks. Okay. But R1 wants to reach those other networks in R2, which are not directly attached to R1. Like, for example, when you are in R2, you have the network going to S3, and you have another network going to S4. Those networks are only directly attached to R2, but they are not directly attached to R1. So for you to reach those networks, R1 must go through R2 to reach those networks that are directly connected to R2. Okay. Now, it is important to note that any network that for a router to reach it, okay, for router R1 to reach the LAN where switch S3 is, router R1 must go through R2. And therefore, any network that a router must go through another router to reach, that network is called a remote network. Okay? So I need to differentiate between remote networks and directly connected networks. Directly connected are directly attached. Remote networks, you must pass through another router to reach it. All right. Now, so those remote networks, remember every router needs to communicate with its remote networks. Okay. But the routers must learn how to reach those remote networks. Okay. Because for the directly connected networks, so long as you have configured the router interfaces with the IP addresses and activate them. For the remote networks, there are 2 ways of adding them to the routing table of each router. One, you as the network administrator, you can manually add those remote networks to the routing table. That's what we'll be doing in the next chapter. So apart from adding them manually, you can also have a protocol, which we call a dynamic routing protocols. Good examples are like OSPF, EIGRP, RIP, BGP, ISIS. You can have those dynamic routing protocols to that will be able to help you to automatically, to help each router to automatically learn the remote networks. That is very important. Okay. You can use the dynamic routing protocols so that you as a network admin, you don't have to manually add the remote networks. You can just enable or turn on that protocol on each router. And then when it's enabled in each router, then the 2 routers will start exchanging the remote networks with one another. And so that is something that we will continue learning. But for now, I want to just go back a little bit where we were. Yeah, we are actually here. So we have seen how the router builds the routing table. Either the router will use directly connected networks or remote networks. We can either add the routes manually, and that is called static routes, which we shall be doing tomorrow, but not tomorrow, on Monday. Or we can do dynamic routes. The router can do dynamic routing using dynamic routing protocols. Okay. And then the last method is what is called a default route. Now, we know that the routing table is not a very big table, okay? And that means it has limits. And so the routing table cannot store all the remote networks in the world. It doesn't have that space. So if you can't store all the remote networks in your router, you can configure a universal route here, okay? A route that can be used to reach all the remote networks, which will not be stored in the routing table. And we call this a default route, default static route. And we will, of course, also talk about the default route later on, okay? Let's look at some packet forwarding mechanisms and decisions, okay? Now, what is being explained here is something we have talked about before, okay? Now, every time a packet arrives on a router interface, okay, the router is going to check one thing on that particular packet. The router is going to check where is that packet going? What is the destination IP address in the packet? Okay. Once it has known the destination IP address on the packet, it starts to compare that IP with the contents of the routing table. So the router finds the longest match prefix on the routing table. It looks for the network address with the highest subnet mask. Then the router is going to encapsulate that packet back into a frame since it is layer 3. So change it back to layer 2. All right. So once the router fixes a new frame, a new layer 2 PDU, and then it forwards that packet out of the exit interface. And like we said, the destination could be another router or a network, and the network or the next hop, which we'll of course talk about. So wherever there's no entry totally in the routing table, then that means that the router has to. So it is important again to just note that this is a process that we'll be studying every now and then, okay? And so, like we said, a packet could be forwarded to a device that is on a directly connected network. That is always if the PC is directly connected to the router interface, or there's a switch connected to the router interface, the whole of that network on the PC or the wireless, it will be operating on just one network. Now, we could also forward packets to the next router, and here the next router is what we call the next hop. So routers could be referred to as hops sometimes. So packets can be forwarded to another router, and that router might have an idea of where the next destination is. So a packet could be sent to the next router, which we are calling the next hop router, so that that router could help us to continue forwarding it towards the destination device. Sometimes, if there's totally no match in the routing table, then the router will always drop that packet. Okay, everything is well planned, and the router does its job the best. The router, it knows very well how to just be able to do its job. Okay. Now, it's important again to just note that packet forwarding decisions is a very important part of the router, because trust me, the routers, they forward so many packets in a minute, in a second. And so there are some packet forwarding mechanisms that are available, and we'll start from a more slower and all the way to a more advanced. Okay, so we have process switching, we have fast switching, and they have the Cisco Express forwarding. Okay, Cisco Express forwarding, the CEF. So let's start with process switching. In process switching, here it's a bit a slow method, because whenever a packet arrives on router interface, the packet has to be processed by the CPU, okay, which is our control plane. And if it matches the destination address within the route table, then the router has to determine the next interface to forward that packet. Okay. Now the only thing is that the router does this when every packet is sent to the router will always forward it, even if the packet is going to the same destination. Okay. Even if there is the same destination, the router will always process this packet. Now, the process of processing each packet, even if the destination is known, is not a very wise one. And so this is too much load that is put on our CPU there. When you look at the second method, which is called fast switching, a little bit older method, but still, very relevant. So for here, a packet that is going to a particular destination, that packet is only going to be processed once. Okay. If a similar packet comes, then this time around, the router has what is called a cache, a fast switching cache or cache, to store the control plane information. Okay, so the fast switching cache or cache, it's where the router will store the mechanisms and the details of that packet, so that wherever the packet is being sent to the same destination, again, the router will just use the details that are stored within the fast switching cache, and it wouldn't need to bother the CPU at any one point. And so that is important. So the information of forwarding that packet will actually be reused to forward similar packets to the same destination. But we do have this last method here, which is called express forwarding. It is the most recent in most current Cisco IS devices. And this particular one, it's normally implemented using two tables. So there's a FIB table, which is the forwarding information based table, and there's an adjacency table. So for this case here, the Cisco Express forwarding doesn't engage the CPU at all. Okay. And what happens is that the information is always already ready in the FIB and the adjacency tables. And so the packet will not be engaging the CPU to do its job. The packet will just be, forwarded using information from the FIB and the adjacency tables. Now, from a mathematical point of view, looking at, I want to give you a small illustration just to be able to understand what I'm talking about. And that is between process switching, fast switching, and Cisco Express forwarding. So let's say you have a mathematical equation, okay? You have a mathematical equation. Let's pick the long division that we learned in primary school. So for the long division, the teacher comes to class, teaches that process, and the teacher gives the same assignment. And every time the teacher brings the same assignment, you are so much used to calculations so that you must calculate the same question. Imagine you already know the answer, but you must expose the question to some kind of calculations. Right? That is process switching. In fast switching, okay, it's like you still have the same question. You do it to the teacher for the first time in class. Then for the subsequent times, when the teacher brings the same question, you don't have to calculate it. What you do is that you just check what the answer was and you write the answer. You don't have to do the longhand calculation again. You don't have to do the longhand calculation again. That is for fast switching. You don't have to calculate that question every time that you receive it. Then the last method is Cisco Express forwarding. For this one, before the teacher even comes to class, you had already calculated the answers of that question and you already know them. And so what happens is that the same question is brought, you had already calculated well in hand, and when the questions come, you don't even need to think. Okay, so you just get the information about the answers and you fill in and you are done with your question. So that is something about the switching methods. Now, it's important to note that we did talk about basic router configurations, and there's nothing that you people do not know here. We talked about from enable to configure terminal, hostname R1, enable secret class. Okay. There's the hostname, enable secret class, line console 0. So logging is normally used to synchronous. Those messages that keep on popping on your screen. Then you have password, Cisco, put the password. And then we have, of course, login, line VTY 024, password, Cisco, transport input SSH, okay, service password encryption, banner MOTD. So these are basic commands, and you can see the ones for configuring IP addresses. To enable IPv6, you need to say IPv6 unicast routing. Get into that interface, and then configure IPv4 address, IP version 6 address, and then no shutdown. Then you can go to the next interface, G001 or gigabit Ethernet 0/0/1, and do the same thing. Go to the third interface, interface serial 0/1/1, and do the same thing. And when you're done, you need to save your work. So you say copy running -config startup -config, and a bit of show commands here. Show IP interface brief, show running config, show interfaces, show IP route, and we're going to use show IP route a lot to view the routing table, and a couple of, these are a couple of verification commands that we are actually seeing here. Okay. Now, having seen this, we also have, of course, these filter commands. I think we have seen them previously. Apart from viewing, for example, the running configuration file, you might just want to view a section, or you might want to only include something or exclude something, or even begin at certain level. So all these are just basically the show commands for our work. So there will be a small packet tracer here, which you will use to, just remind yourself of the basic configuration commands. And that is something that up to now, you should be able to do. Now, I want us to check on the routing table, because the routing table is everything. And you need to know how to read the routing table. That is a big deal, ladies and gentlemen. You must know how to read the routing table. And so, like I had told you, that a routing table can be computed from different sources. It can either be the directly connected networks. I already showed you. You just configure the interface IP addresses and activate them. They can be remote networks, can be configured through static routes by manually entering the remote networks, or it can be configured dynamically by using dynamic routing protocols like OSPF, EIGRP, so on and so forth. So within the routing table, you will always find some codes or letter codes. Okay, it can be L, can be C, it can be S, O, R, so on and so forth. And so each letter normally represents something. For example, if you see letter L, L means normally the local interface of the directly connected network to the interface IP address. C is always the network address of that directly connected network. So two things, when you configure an interface with an IP address and activate it, the data records two things. First, it will record the IP address you had configured, and two, that is with L, and then it will record the network address where your IP belongs, and that will be given letter C. Then you'll see letters like S, which basically is for static routes. O is for OSPF. Asterisk, or the star, is basically for default routes, and we will see again what default routes are. Now, at this point in time, I want to take you guys through how do we read the routing table, and this is very important. The routing table have the following things. It does have these letters. Let me just zoom in here so that you guys can be able to see it. Correct. So this is the routing table, and they have been given numbers here. And this is how we always read the routing table. Normally, the routing table is read vertically. Okay. Okay. So let's look at column number 1, and they're normally the same for both IPv4 and IPv6. Okay. Now, if you look at 1, then it means that 1 is always the column number 1 is always how the route was learned. How was that remote network learned? And how the route was learned will always be, that part will always just have letters on column 1. Okay. It will just have letters where if you see O, like you see the O that is there, you know that that is OSPF. If you see D, you know that is EIGRP. If you see R, that's RIP. If you see S, static route, so on and so forth. So how was the route learned? Was it learned statically? Okay. Column number 2, sorry. Column number 2, I just want to zoom out this. Okay. So column number 2 is actually the remote network that was learned. Okay. Which is that remote network that was actually learned within our network. So that is always column number 2. Then we have column number 3, and the column number 2 will always have a network address with the subnet mask put in form of the slash notation. Like this is for network 4.0/24. Then column number 3 and 4, they'll always be in a square bracket and separated using a what? A forward slash. Separated using a forward slash. There will be 2 numbers inside there. The first number is called an administrative distance. The first number is called an AD, administrative distance. An administrative distance is the trustworthiness, how much that route is actually trusted. So the trustworthiness of a router to use a certain route, or the trustworthiness of a certain route, is what is called the administrative distance. It's a unique value. Normally, each and every protocol has its own AD, administrative distance. Okay, and it is just the trustworthiness, that value, no units. It just indicates how much that route is trusted. Then the number after the forward slash, which is 50 in this case. By the way, the 110 you see there is for OSPF. OSPF is 110. We learned that EIGRP is 90, for example, so on and so forth. So the next number after the forward slash, number 4, is called a metric. It's a metric. Okay. So metric, which is part 4, metric basically is the distance to reach that particular network. And this distance is not measured in kilometers. No, it is not measured in any of those other units. It is just a random values calculated using the protocols. So the distance to reach that network is what is called a metric, and 50 is there. Then you go to column 5, which normally has what is called the next hop IP. A next hop IP is actually the IP address. Let's say this is router R1, and router R1 is connected. This is router R2. And so that is R2, and a message is moving from R1 to R2. Okay. Remember, every router interface must have an IP address. So if a message is moving from R1 to R2, obviously the message will have to enter through this interface here. Okay. The interface where that we use to enter this router through. So the IP address of that interface is what we call the next hop IP address. Okay. The IP address of the next router on the way through which traffic enters, we call it the next hop IP address. Okay. Then we go to column 6. Column 6 is basically a timestamp. How much time has elapsed since this remote network was learned? Since this network was added in the routing table, how much time has elapsed? That is 6 is a timestamp. Then the last one is 7. 7 is always the exit interface. We know that when traffic is leaving R1 or network router 1 to go to 2, the interface through which traffic leaves the router. Okay. So the interface through which traffic will leave R1 to go to router 2, it's called the exit interface. All right. And so column 7 will always be the exit interface, the exit interface. So please do mark next hop and exit interface. Next hop is IP, which is next routers. For the next router, we don't talk about the exit, the entrance interface. No. Exit interface, the next router is the next hop IP. And the same thing will always be in IPv6 routing table. Number 1 down here, because number 1 is how the route was learned. Number 2, of course, is the network address there, and the prefix length. And number 3, of course, is the administrative distance, and number 4 is a metric. Number 5 is actually the next hop, and number 6 seems not to be here. Okay, so number 7 basically is the exit interface. And so it is important that you know how to read. This is something you'll be doing almost every day. When dealing with the routers, you must know what are some of the routes that are available within the routing table. And for your exam, there are going to be so many questions testing some of these concepts. Now, we already talked so much about the directly connected networks, and we talk about letter C and letter L, and we don't have to repeat that. We also talk about static routes, whereby you manually add remote networks to the router. Okay. So the static routing, in most cases, is very suitable for small networks, which are not expected to grow uh, uh, very fast, very soon. Okay. So it's very suitable for small networks with very few routers. So it's static routing. Sometimes you can just use a single route or a single default route to be able to represent so many paths within the internet. Okay. So we'll talk about, of course, what is a stub network, and you know, routing from and to a stub network. A stub network, by the way, is just a router with only one exit to the internet. Okay, it doesn't have any other connection. So these static routes, looking at an example or a diagram like this, you see we have two routers here, router R1 and R2. R1 is directly connected to two networks. And at this point in time, you need to know how to read your networks. Okay. So in this diagram, R1 is directly connected to network 10.0.1.0. That's how we read the networks, and that is the name of that network. And R1 is also directly connected to 10.0.3.0/24 network. R2 is sharing the same network of 10.0.3.0/24. And R2 is directly connected to 10.0.4.0/24. So it is important to note that R1 has only one remote network, which is this network here. And R2 also has only one remote network, which is this one here. Okay. So once that happens, you as the network administrator using commands like this. In R1, you want to add network 4.0. So we'll say IP route 10.0.4.0, put the subnet mask, which is 255.255.5.0. Then you might need to put the next hop IP. And from R1 going to R2. The next IP is the IP address of this interface here. And you can see it's given .2. So if you are ever given this .2 here, it means the name of that interface is 3.0.3.3. Okay. So 10.0.3.2 is the address that is actually here. So this 2 is normally used to, to be able to replace it with the 0 there so that you can see your exact IP address here. So you'll do that for each router, add their remote networks, and you just use IP route, and this is how you actually get to add the remote networks. For dynamic routing protocols, having these two diagrams here, we realize that R1 is directly connected to 3 networks, R2 is directly connected to four networks. Okay, because R2 is connected to S3 to S4 to R1 itself and also to the internet. And so what happens is that the way dynamic routing protocols, once the protocol is enabled in R1 and R2, they start to talk. Like listen to what R1 is saying, that I will share with R2 all the networks I know without about and tell R2 when there are many changes. So R1 is gonna tell R2 that Mr. R2, I know how to reach network 10.0.1.0, 10.0.2.0, and network 10.0.3.0. So R2 will receive that message, and R2 will also tell R1 that R1, I know how to reach 3 networks, 10.0.4.0, 10.0.5.0, the route to the internet, and the link connected to R1. Okay. So R2 will also advertise and tell R1 to learn those networks. And so at the end of it all, R1 and R2, they know all the remote networks that the others will be having. Okay. And so the routing table and how these dynamic routing protocols work. We are going to talk majorly about static routing on Monday, but in the third module, we begin by the first 2 chapters is all about the OSPF, which are dynamic routing protocols. Okay, the open shortest path first. So of course, we do have what's called the default routes. I will show you, of course, how to configure default routes. within your network. And I'll give you more and more illustrations later on. I did talk about administrative distance, and I said this is the trustworthiness. Okay. The trustworthiness, the trustworthiness of the route. Okay. And we have seen the longest march. We also have, when we're dealing with the administrative distances, the routers will also always choose the lowest AD. A router with the lowest administrative distance. If there are different routing protocols, then the router will always choose the router with the highest, with the lowest AD. With the lowest AD. Now, you can see a group of administrative distances here. You can see that directly connected networks have an AD of 0, all of them. Static routes have an AD of 1. EIGRP summary route 5. External BGP is 20. 90 is EIGRP internal. All right. OSPF is 110, as we saw. ISIS is 115. RIP is 120. And external BGP, of course, is 170. And the internal one is 200. All right. So you need to have at your fingertips some of these values so that you are not on the wrong side. Now, as we basically come towards the end of this, we could be asking ourselves, which one is better? Okay. Is it static routing or it's dynamic routing that is better among all of them? Okay. And it's a question that you can always ask yourself, and see really how does it get to work out. Okay. Now, each of them has advantages. Okay. Each of them have advantages and disadvantages. And that's why it is important that we study both of them. In most cases, you'll always find them being used together. That's why we say they are mutually exclusive. They are not mutually exclusive. You'll always find them being used together. Okay. And so that's why it's very, very important for us to be able to learn them. So static routes are commonly used as a default route to forward packets to the service provider. Very, very important. And static routes, you can also use them for routes that are outside of your routing domain that are not learned by the dynamic routing protocol. That is very specific. Okay. And sometimes when you want to configure a path that you don't want it to change, if you don't want a path to change, then you are going to configure your path using a static route, because static route is like a manual route. You can compare this with DHCP, for example. We have DHCP where the dynamic assignment of IP addresses, and then the other one is called manual assignment or static assignment, where with the IP address assigned on a device, it will not change. It will not actually change. And so it is important to just be able to check that everything is actually configured really well. Now, sometimes when you want to route to a network that only has one outlet, which means it only has one connection to the internet, static routes have become one of the best routes here. Okay. Now, someone can also say that static routes are very useful in smaller networks. Okay. But you cannot remove dynamic routes for smaller networks. Okay. But static routes can also be used, both static and dynamic can be used in smaller networks. But if you have fewer routers, always go for, it's easier to go for static routes. But when you start having bigger and bigger networks, then the best one will always be the dynamic routes. The dynamic routes will always be the best for bigger network. Now, static routes provide some level of security because in static routing, we don't have exchange of those messages among the routers. No, because everything is done manually and there's no movement of the packets. If you compare that with dynamic routes are preferred on networks that are more than just a few routers, that is several of them. And when a change in the network diagram requires the networks to automatically determine another path, that is when you might need this dynamic routing. And it is very scalable. The dynamic routing protocols, they can accommodate as many routers as possible. And that is something, again, very important for us to note. And therefore, it is important that we do a comparison among the two of them. Is it static route or is it dynamic route? Okay. Now, in terms of configuration complexity, the dynamic routing protocol, the complexity will depend on the size of the network. If the routers are few, it will be much easier. But if there are many, then you need to do a good job, right? And the complexity, I let me just reframe that, okay? Since dynamic routing protocols, it's a protocol that once you install it, it does not matter whether you have many routers or few routers. The complexity does not always change, whether you are having a bigger router or a smaller router. But in static routes, since it's a manual way of doing things, anything manual, the more time it takes, the less efficient it becomes. And that is something that we need to note. So the more routers you include in a static routing, the more problems you're calling for yourself, because you're bound to make mistakes, you're bound to configure wrong routes, you're bound to leave some routes not configured as well. Now, wherever topology, the network diagram changes in dynamic routing, the topology will, the dynamic routing protocol will automatically adjust to the topology. But in static routing, you, the network admin, must intervene. You must manually go and set up things if there's a topology change. In terms of scalability, the dynamic routing protocol is suitable for both simple and complex networks, but static routing is only suitable for smaller networks with few routers. And like I've already mentioned, dynamic routing protocols are very insecure. They don't have enough security because of the exchange of the messages, it does change. Since static routing does not exchange those routing updates and messages, they don't have any security issues there. So they have an inbuilt security because of lack of exchange of these messages. Now, because in dynamic routing protocols, we have so many messages that have to be exchanged. There are a couple of elections that will also be needed. There's a lot of resource usage in dynamic routing protocols, unlike in static routing, where there's no additional resources needed. Then to predict the path in dynamic routing, the path will always depend on the current topology, okay? And the protocol used. But in static routing, the path is always manually defined. And so the path remains as it was configured. As it was configured, the path will always remain. Now, there's a couple of these dynamic routing protocols, and this started way back in the year 1982. So in the year 1982, we had EGP, that's Exterior Gateway Protocols. Then we went to IGRP, Interior Gateway Routing Protocol. Then in 1988 is when RIP version 1 was born. Okay. So RIP, which is the Routing Information Protocol, was one of the protocols which it RIP can only accommodate up to about 15 routers. That's a very small networks, and that's why RIP is not very common. So when you came to the 90s, several of them were actually invented here. We can see ISIS way back in 1990, the intermediary system to intermediary system. And when you go to 1991, OSPF version 2, which is for IPv4, was born. And this is the OSPF will be configuring the next module. In 1992, we had EIGRP, the Enhanced Interior Gateway Routing Protocol, was born here. Then version 1 was of RIP was upgraded to version 2 in 1994. And then BGP for communications between their service providers and their clients. We had BGP, the Border Gateway Protocol. Then RIP for IPv6, which is called the RIP Next Generation. RIP Next Generation was born in 1997. In 98, we had the multi-protocol for BGP that uses both IPv4 and IPv6. And so the development in the 90s was amazing. Since in 1999, we now started adding OSPF version 3, which is for IPv6. Okay. And so in the year 2008 or 2008, we had intermediary system to intermediary system also launched their version for IPv6. Okay. And the journey has been worthwhile. And we still have these protocols very strong and helping routers to communicate dynamically, helping routers to communicate dynamically. Like I've already hinted to you, these protocols, we have those for IPv4 and those for IPv6. And we have two broader categories. We have the exterior gateway protocol or EGP. Here we only find BGP, which is a path vector protocol. BGP for IPv4, version 4, and BGP multi-protocol for both version 4 and version 6. Then we have the interior gateway protocols. This is where we have the RIP version 2, which is for IPv4, and RIP next generation, which is for IPv6. We have EIGRP as another distance vector protocol, and EIGRP for IPv6. So it's important to note that RIP and EIGRP are both called distance vector protocol. And OSPF version 2 and version 3, IS and IS for IPv6. Those are actually linked state routing protocols. So OSPF and IS, intermediary system to intermediary system. OSPF means open shortest path first. Open shortest path first. So these are basically dynamic routing protocols. These are the ones that can enable routers to exchange packets or to be able to land the remote networks automatically without the intervention of the network admin. Okay. Now, the major work of these dynamic routing protocols basically is is to discover remote networks. Okay. All those remote networks, without manually adding them, you can actually just use dynamic routing protocols to land them. They also make sure the routing table is kept accurate and up to date, very important. And wherever the current path to a certain destination network is not available, dynamic routing protocols can help in choosing the best path to the destination network. And finally, these protocols have the ability even to find a new best path if the current path is no longer available. We say that, but choosing the best path to a destination network, very, very important. Now, I wanted us to bring this basically to a close, and by just talking a little bit about our protocols. The dynamic routing protocols have a few things in common, and one of them is that they have some data structures. We call these tables, okay? Or they are actually tables or they are databases, okay? And this is where they keep most of their information, and that information or those databases will always be stored in the RAM. apart from the data structures, which are the databases and tables, the dynamic routing protocols also have some messaging, and that is a big thing. Okay, they use some kind of protocol messaging to exchange information among themselves. Okay, and if they need to do some election, for example, they use this messaging. And finally, each protocol has an algorithm, which is basically a list of steps that are used to accomplish a certain task. So each protocol has its own algorithm. Like the OSPF has an algorithm called SPF, the shortest path first algorithm. EHRP has what's called dual, the dynamic uh, update algorithm. So, I mean, we'll talk about, of course, those particular algorithms. The messages are very, very important, and we learn about the different types of messages within OSPF, the different types of databases, and even the algorithms. Okay, and just to before we get going, is that choosing the best path is something that is very important for the router, and the best path could be chosen based on the value or the metric that is used to determine the distance. And it could be a metric, which is normally just a value used to measure the distance to a given network. And so dynamic routing protocols, they use their own rules and matrices or metrics to build and update these tables. And so looking at, for example, these ones here, like RIP as a dynamic routing protocols, the routing information protocol, its metric is a hop count, like how many routers along the way to reach the next device or the next network. Okay, and it can only go up to about 15 hops that are allowed with this protocol. So this protocol RIP, it is only used in smaller networks. Then when you go to OSPF, which uses a metric called cost, which is based on some accumulated bandwidth from the source to the destination, such that the faster links are always having lower cost, and the slower links, of course, have a higher cost. But the routers prefer the lowest cost normally, and the lowest cost has the highest bandwidth. And then we have protocols like EIGRP, the Enhanced Interior Gateway Routing protocol. It calculates in metric based on the slowest bandwidth and delay values. And sometimes it will use together with the load and reliability on its calculation. But the slowest bandwidth and delay values are very crucial for this dynamic routing protocols. Now, some of these protocols could do load balancing and some of them don't, okay? So load balancing, again, is when a router has two or more paths to the destination, and each of them have equal metrics values, and therefore it means the router can forward packets through both ports, okay? So when packets are being forwarded using both paths equally, then we call it equal cost load balancing. Equal cost load balancing. And so sometimes there might be two different metrics to the different routes, So if there are two different metrics, it means one will send more than the other, okay? And so equal cost load balancing is not going to happen here, okay? And so protocols like EHRP normally support an equal cost load balancing, where packets are being sent through one particular route and not the other route. Now, I think this will form a very good place for us to end this. And I'm aware that, today being a Friday, you guys might have your own plans. So I would like us to end this here, and we'll meet next week, basically, to be able to continue and do routing, static routing, basically, and configure it.